Okay. So, hi everybody. Thanks for the nice introduction. My name is, as you said, Noah Brucker. I'm a PhD student at the University of Zurich, under the lead of Professor Laura Baudis, and I'm working together with Ilya Charaev on superconducting nanowire single photon detectors. And in the next half an hour, I will tell you something about how we use SNSPDs in the search for light mass dark matter, and how we can use them in the future for future collider at CERN, for example, the FCC for high critical temperature superconductors. But before we start, who cares, right? Why do we need these faint light detectors? It sounds very niche that we want these single photon detectors, these faint light sources, but in fact, a lot of current research topics use these faint light sources, these single photon regimes. Quantum key distribution, space-to-ground communications, and even everyday devices, such as the newest iPad and iPhones, they have LiDAR sensors, which especially need these sensors. What do have all these fields in common? They have low noise, the single photon quantum, and they can detect low energy. And as a coincidence, even one of the biggest mysteries in physics needs exactly these properties. So we care for the dark matter detection. Now, dark matter is one of the biggest mysteries in modern physics. Basically, 90% of the matter in the universe belongs to dark matter, dark energy, but we weren't able to prove it. We have strong evidence that it has to exist. For example, gravitational lensing or dispersion velocity of galaxies. The problem with dark matter, as we assume, it's neither absorbing nor emitting the light. A lot of big dark matter experiments they strive for high energy, high mass particles. But what if the dark matter particle is not heavy? What if it's light? Let's say it's in the milli-electron volts or in electron volts range. So the focus shifts from high energy, rare events, to low energy, low noise. And here, especially, come the quantum detectors in play. And the current state of the art for quantum detectors is we can more or less separate them in three topics: photon multiplier tubes, the single photon avalanche diode, the SPAD, or the superconducting nanowire single photon detectors. They have mostly 5 properties, such as the system detection efficiency, the noise, the timing jitter, the cutoff wavelength, and the count rate. As we can see here on this image, in comparison to the photon multiplier tube and the SPAD, the SNSPD is perfect in any sense, basically. For example, the system detection efficiency is 98%, which is basically every particle that hits our detector is transformed into a signal. The noise, we have 10 to the power of -6 count per second as a noise level, which is very low. The timing jitter is in the picoseconds range, and the cutoff wavelength, which corresponds to our energy, is currently at 29 micrometer, which corresponds to a photon energy of about 40 millielectron volts. So, therefore, the superconducting nanowire single photon detectors is a very promising detector which can be used for dark matter detection. But how does a SNSPD work? Well, imagine it's a superconducting nanowire. So basically, when we apply a current, we have no resistance, so we have no voltage. Now, if a photon or any particle hits our nanowire, it deposits energy onto our nanowire. This energy deposition leads to a hotspot creation on our nanowire, which then locally breaks superconductivity. Then it switches back to normal conducting mode. Since we apply a current and we are normal conducting, we have a resistance and we have a voltage peak. This voltage peak corresponds directly to a signal, either dark matter, a photon, or sadly, noise. After a short amount of time, so after nanoseconds, the nanowire switches back to superconducting mode and is ready for a next signal. Superconducting nanowires are first developed in 2001 by Goltzman. And originally, they are very thin wires. That's why they're called nanowires. They are in the nanowire regime, so 50, 60 nanometers wide. But in the last 5 to 6 years, we were able to increase the effective area of these nanowires to micrometer squared area. And even the thickness could be in the micrometer width. The problem is we cannot just scale this up. We need, since we are in the low energy regime, we need a high target mass, because if not, we were not able to detect anything. So how can we increase this area? This is very difficult because it induced a lot of problems into the creation, because the electron sputtering systems and all the devices, they're not made for these huge areas. They are made for nanowire nanowire, nanometer width, and nanometer thickness. So this problem, this field of increasing the area led to a whole industry all over the world, leading in creation of SNSPDs. So even in Switzerland, we have the ID Quantic, which is located in Geneva, which produces SNSPDs, or in Germany with the Munich instruments. And all over the world, they're striving to increase the area of these SNSPDs, which then corresponds to a larger mass or larger active area. And this, well, this fight of who is the best lead to astonishing results over the last decade. So when we compare the results in 2016, which is now freshly a decade old, we see that, for example, the efficiency jumped from 93% to 98% in the last, well, 9 to 10 years. The dark count rate from 4 per second per square millimeter jumped to 4 times 10 to the power minus 5 per second per square millimeter. The active area, we could basically increase by a factor of 100. If we project this results to 2030, we can even reach the first centimeter squared of a detector. If we check what happened in the last 1 or 2 years, probably we will even exceed this result in the next, well, 4 or 5 years. So SNSPDs are not something new, something obscure anymore. They are new detectors, they are used, they're promising new detectors. And in the next, well, in the second part of the talk, I want to explain a little bit how we use them in SNSPDs, in dark matter research, or how they can be used in the FCC, which is the Future Circular Collider, which is a 100-kilometer diameter ring, which I want to build at CERN, which will use the LHC, the current ring, as a pre-ring, basically. So, okay, and why is the SNSPD good for dark matter research? I already told you that, and the mass range of an SNSPD can range from 0.1 milli-electron volts to 10 eV. So this is quite low. This is quite a low value. But how does an SNSPD detect dark matter? There are, in principle, 2 ways. The first one, because the SNSPD is located, the detector is located on a substrate, the dark matter can hit the substrate, and therefore, through the absorption of the dark matter, it can emit a photon. This photon hits our SNSPD, then it creates a hotspot, then we have a signal. The second way is that the dark matter hits directly onto our nanowire, and then get either absorbed or scatters off of the SNSPD. In both ways, they deposit energy, creates to a hotspot, creates a signal. In both ways, depending where it hits, we see a voltage peak in our signal, and we know we had a hit. And this comes to the one standing out features of SNSPDs. If you compare, for example, LC or Xenon, the huge dark matter experiment, they have a huge target. Xenon, for example, uses hundreds of liters of liquid xenon, which is not only horribly expensive, it uses a lot of space. The big advantage of an SNSPD is that it is the target and the sensor simultaneously. We want that the dark matter particle hits our SNSPD, because when it hits the SNSPD, it deposits energy, and at the same time, it gives us a signal. This signal then is the sensor. And to make this work, to make an SNSPD work for this research, we have to have 4 topics or 4 problems which we have to solve. The first one is the large mass, as I already told you at the beginning. The second one is we need to be able to detect mid-infrared photons. The third one is we have to have reduced the dark counts, well, basically the noise. And since we never can reduce the noise to 0, we need to know where this noise is coming from. And here on the bottom right, I have included a picture which corresponds to the state of the art for current dark matter experiments. So you can see Xenon, which is still, in my opinion, the leader in dark matter search. But at the top left, there's the new experiment, which I'm part of. That's why my t-shirt, which is the crocodile experiment. We are not yet. Yes. So basically, on the x-axis is the WIMP mass. So basically, the dark matter particle, which mass they have, and here the cross section between the dark matter and the standard model particle. So you want the cross section to be as low as possible, basically, to have the lowest energy as possible to detect. And this may be a strange plot, but I just want to show you that the crocodile experiment, it's a rather new experiment. We are already in the field to be comparable with the other experiment. But what is the crocodile experiment? basically, you want to have a low as possible, let's say, threshold.
Threshold.
Yes, you want to have because when you have the threshold low, you have cross-sec low, you can say until then, basically, you are sensitive.
Yeah.
That's basically the idea. Yes, and at the end, yes, if it's too, let's say, too bad of a precision, you detect nothing, or you are not nothing new. So the Crocodile experiment, it's short for Quantum Resolution Optimized Cryogenic Observatory for Dark Matter Incident at Low Energy, which is a very catchy name. That's why we abbreviate it to the Crocodile experiment. And it's a collaboration between a lot of universities all over the world. Mostly the people are located at the University of Zurich, but we have the theoretical part is located at the MIT in the US. And some of our analysts are sitting at the Hebrew University of Jerusalem. And our detectors currently are coming from the Karlsruhe Institute of Technology in Germany. If you want to check out our website, at the top right, I put you the link. To achieve our 4 problems, or our 4 requirements, as I mentioned already before, we need to have a large mass. We need to have a large active area because we want to detect these low energy particles. Now, it's not just scaling up. The problem is when we make the nanowires wider, we can have current crowding effect. We can have edge defects of our nanowire. The thickness cannot be uniform, and this all leads to defects in the nanowire. This leads to noise. This leads to random breaking of superconductivity, to false signal. So our goal is to create a large scale SNFBD with a large active area with as less defects as possible. This isn't trivial. We are working on that with different companies all over the world. And the current chip we have is called Crocodile 1.0, and it's a tungsten silicide chip with 45% of tungsten and 55% of silicon with a thickness of 8 nanometers and a detector area of 600 by 600 micrometers squared. The wire itself is 1 micrometer. And at the bottom right, you can see basically like an easy sketch of our detector, where we have a huge substrate of 380 micrometer silicon, and then a tungsten silicide detector layer encapsulated between 2 silicon dioxide layers, which are mainly there for protection. And then we are using, and this detector is located in a fridge, in a cryostat, cooled down to 100 millikelvin. And we are using quantum cascade laser, which emits wavelengths of 5 and 11 micrometer onto our detector. This corresponds to 200 approximately and 100 milli-electron volts as a threshold. Now, how do we know that we are sensitive to mid-infrared detection? So basically, here this plot shows you the count rate, the normalized count rate as a function of the bias current. As you can see, when I increase the bias current, at the beginning, we basically have 0 hits. At a certain bias current, the count rate goes up rapidly until it reaches a plateau. When we reach this plateau, we know that our detection efficiency is close to 100%. What does a detection efficiency of 100% mean? That every particle that hits our detector results in a signal. So we are not losing any signals. 100% is still very optimistic, but we are close to that with 97, 98%. And then we want the opposite, which is the dark count rate, which can be basically count as the noise, as the background. And this is, again, black is the photon count rate I showed you before. And in red and blue, you can see the background for 2 different detectors. This is not the same data as before. I just want to show you because I think this plot explains it very well. So you can see for a low bias current, the noise is quite low. It's 10 to the power of -4. And after getting close to the critical current of our device, the noise level increases by a lot. And at a certain point, it's basically on the same level as the photon count rate, basically destroying our signal and making the measurement useless. And we can separate it in 2 backgrounds. The first is intrinsic dark count. So basically, we're taking the same measurement as with the photon count rate. We place our detector in the fridge. We bias it to a certain current, and we are not using any laser light. In theory, we shouldn't see any counts, but as always in physics, it's never that easy. So we still see some counts. These are the intrinsic dark counts. The second dark count is called the background dark count, coming from electronic noise coming from, as I mentioned, the constriction of detector, of the how it is built, how it's the stoichiometry, the bias current, and most of this noise coming from the electronics. Because keep in mind, we are using microamps or even nanoamps for certain detectors. Most current sources we have at the university currently still have a lot of noise, which lead to false counts. So the idea here is to have good fiber coupling to reduce the noise, a better chip to reduce the noise as well, to keep the noise as low as possible. But low as possible doesn't mean zero. So we did a measurement with our current chip for 415 hours. And in 415 hours, we were able to detect 15 individual non-periodic pulses. Now, the big $1 million question is, what are these 15 individual pulses? I would say dark matter, but it's not that easy. So we have to find out where these 15 events come from. For this, we have two methods. The first one is we are going underground. For this, we have partners at LNGS, which is the Laboratorio Nazionale del Gran Sasso in Italy, which is an underground laboratory with 1,500 meters of water equivalent underground. With this, we can reduce the cosmic rays to, well, basically zero, and the fridge can cool down to 8 millikelvin instead of 100 millikelvin for our device, which will reduce the stray photons and the thermal photons as well. The second one is the so-called GN4 simulation. GN4 is a simulation toolkit provided by CERN, which lets you simulate the trespassing of particles through the surfaces and calculates your deposited energy onto your holder and tells you if a particle has enough energy deposited to give you a hit. With these two, I think we are on a good way to understand where these backgrounds are coming from. And basically, we have the first results, which are even from published in a paper, as you can see at the bottom, where we have the electronic scattering and the electronic absorption. And you can see blue are the previous results, the previous SNS results, and green is our crocodile experiment. As you can see, the cross-section a little bit lower, but the energy at the bottom is quite lower than the previous signal. And if we know, this is just a far stretch, but if we know where this background is coming from, we can reduce the signals even more, both for scattering and for absorption. Now, switching to the second part, the potential use case in the FCC. As I mentioned before, the FCC is the Future Circular Collider at CERN, which they start building, I think, in the next decade, and they want to finish by the end of 2050 or something. It's a 100-kilometer large ring. They want to have these SNSPDs as detector because we were able to measure the first mega electron volt electron with an SNSPD. The problem is certain materials, such as tungsten silicide, they need operating temperatures of 100 to 200 millikelvin. That's expensive. That needs a lot of helium, and for such a huge magnets they have, this will cost a fortune. So they are planning to use different materials, such as MgB2, molybdenum silicium, or even YBCO detectors. And for this, I have here our setup which is located at CERN. You can see at the top right, this is our telescope which we are using for our SNSPDs. They're located in the middle. And basically, we hold these SNSPDs into the beam of the SPS to see if we can detect the signals. And keep it in mind, that's a very preliminary work. That is just the first run. So even these results here, they are fresh released. So keep that in mind. On the left, we have the amplitude distribution where they use the previous detectors, the LGATs, in comparison to the SNSPD. As you can see, the SNSPD has a way higher amplitude in comparison to the LGATs, which is good. So we can have less noise sensitive devices, which is good. But the problem is, if you compare the count rates or the events for the SNSPD, which is here in black, it's basically 50%. This has probably due to the rise time, because the LGATs are way shorter in the rise time until they switch back to superconducting mode. So I'm guessing we are losing a lot of signals here with the SNSPD, but it's just preliminary. I just want to show you that in principle, it is possible to use SNSPD to detect these particles at CERN. As I mentioned at the beginning, the operating temperature of an SNSPD, in my case, is about 100 millikelvin. But if you compare how an SNSPD started in 2001, where they were like at 4 to 5 Kelvin for certain temperatures, in 2025, we were close to 25 Kelvin. So our plan is to increase the operating temperature of an SNSPD as high as possible to find a certain material that we can use to detect these particles or to make it superconducting. And here I have a comparison between the amorphous polycrystalline and the cuprates. So I'm using, for example, the amorphous SNSPDs, which is below 5 Kelvin, but even the polycrystalline ones. And a very promising new type of material are the cuprates, YBCO and BSCCO. They have critical temperatures of about 70 to even 80 Kelvin. The plan here, just to say, is that cryogenics has to be more reliable, easier, and more cost-effective, because they need to lower the price of these devices. But then, why not just use cuprates? Well, it's never that easy. This is not my field of topic, but I just want to show it a little bit to you. Cuprates are really hard to manufacture into SNSPDs. As you can see here, they need a lot of different layers. They need a lot of different materials. They are not trivial to produce. But still, we have some cuprate SNSPDs. But as you can see here, these are the first results for some LCO, BSCO detectors. And as I compare to the previous plot I showed you with the photon count rate, we are not able to reach a plateau yet. So the moment it switches, we have no high detection efficiency. We are still in the 80 to 90%, which is still too less to have good signals. But it's a promising new approach. And then another material which we are working with currently is MGP2. This is even freshly released on 2024, 2 years now. And even here with this material, we have no high detection efficiency. We have no count rate, which is stable at a certain point. So in the future, we have certain materials we can work with. I just want to show on the last few slides here that SNSPDs, the research SNSPDs, is nowhere near over. We have new materials. We have promising new approaches, high temperature SNSPDs, which can be used even in different applications. And yes, with this, I'm at the end of my presentation. I want to thank everybody that works with me, mostly at the University of Zurich, but even at the MIT. And I want to thank all the people at the NASA JPL laboratory for their help creating these big detectors. And I also want to thank the Laboratorio Nazionale del Gran Sasso for their help, for the time in their underground laboratory. And yes, so thank you for your attention. If you have questions, please.
Thank you.